Thank you very much for having me in this series. I'm super happy for presenting our work. Thank you very much also to HDRN and to Kim who gave us support throughout the conduct of this research. So what I'm going to present today is a joint work with Jean-François Etier, who's been involved with HDRN for quite some time, and two of my students, Simon and Marie-Pierre, and an assistant professor, Klaus, who's a theoretical statistician at the University of Sherbrooke. And so the title of my talk involves, well, distributed statistical analysis, and this is a fairly unprecise, I will say, thing to say, because we'll be mostly concerned with what's been called here in this series horizontal federation. So we're going to talk about statistical methods that allow to analyze data that are horizontally partitioned. So just to recall, so an horizontal partition is where the data is stored at different locations, and so it cannot be centralized. And so the partition that belongs to a node, it has all the data that belongs to a given individual, and but different nodes have data about different individuals. But each nodes possess the same variables. Okay, so we're talking about, basically, we have a common data model per node. And so when we started to work on the topic of horizontally partitioned data analysis, we soon realized that it wasn't totally a new research stream, because that topic had already been investigated in another stream of literature in statistics, which was the setting of massive data analysis. But there are some differences between the application of statistical methods for horizontally partitioned data and the massive data setting. So in the massive data setting, there's basically a large data set that is on a server, but the data set is too large to be processed on that server. So the data is partitioned on several machines, which are then able to compute summary statistics, which are then sent back to the central server, which aggregates them to produce the final result. So this is we're talking about distributed computation. So the massive data setting, it shares similarities with the setting where we hope to use distributed statistical methods to analyze horizontally partitioned healthcare data. But it also has different important differences. And one of them is that in healthcare, we don't control the distribution of the data in each site. So, for example, there are data centers that might have that might involve different type of individuals with different characteristics. For example, centers that might collect data from older people, and this has impact when you talk about computing confidence intervals and making hypothesis tests. So this is just to give you an overview of where we're going with that presentation. So when we dug in this topic, so we first realized that there were many methods available. So we started to, so our first goal was to review which methods were available, and then to assess which ones are applicable to the healthcare context. And of course, we would have liked to make a list, to make a list of all the available methods, but assessing the applicability of statistical methods to a given context is a task that is fairly difficult. So we focused. So we will focus for this talk on generalized linear models. Okay, and we'll see that methods that are available, some methods that are available needs to be adjusted to to take into account the particularity of healthcare data research. All right. So this is a work that you can find on an archive, a paper that is currently on archive, and yeah. So here's the context of the talk. So we're concerned about so we want to do an analysis that involves n individuals, and the data from these individuals are not stored at a single source. Instead, they are partitioned among k locations, which are called here nodes. And the particularity here is that data cannot be centralized. And of course, one application of that type of setting is multi-jurisdiction data, where laws or ethics prevents centralizing the data. And so here we focus on horizontally partitioned data, where each site shares the same set of variables as all other sites and holds a specific separate subset, which is said to be a partition of the analytical data set of the n individuals. And so just to give you a picture of an horizontally partitioned data set, I guess the name is closely related to how we usually set a database in, for example, in an Excel spreadsheet. So usually you would have the individual in lines, and you would have the variables as columns. And so when we talk about an horizontally partitioned data set, this means that you are partitioning your Excel spreadsheet into k different partitions, and the particularity is that you don't want to share the individual data. You cannot reconstruct your whole spreadsheet. So instead, you will basically calculate summary statistics to be exchanged to a coordinating center, which will then aggregate in some way the summary statistics that are shared by every node. And so here we assume, which is a common assumption for a statistician, but which is a very strong assumption for a practitioner. And we will assume that the variables have the same syntax and the same semantics. So this means that there have been a lot of preprocessing work done before thinking about applying these statistical methods. Okay, but we assume that this has been done, and now we're really focusing on what are the type of statistical analyses, statistical inference methods that we can do in using data that possess this structure. So the question is, how can we perform statistical inference procedures? And by this we mean compute confidence interval and do hypothesis testing on horizontally partitioned held data. Okay, so and so we will see that there are many methods that exist. So they differ by the quantities that are shared, and they differ by the number of communication rounds that are made between the central server and the nodes. And so we'll be interested in comparing them on the information that needs to be shared in order to make the model parameter estimation. And then we'll compare them in terms of their operational complexity. So a method that only requires one round of communication between the nodes and the central server, so the coordinating center, is much less complex than a model which requires many iterations between nodes and the central server. Of course, if you have an infrastructure that allows making those computations, and you don't need to exchange quantity by email, then this can facilitate the analysis and reduces the importance of the operational complexity. So what we will cover today, so in the presence of horizontally partitioned data, what are the available statistical inference procedures? And of the methods that are available, we'll be looking at so when we focus on generalized linear model based analyses, um, which are the ones that are applicable to the analysis of healthcare data. So as I mentioned before, a large stream of literature that has contributed to the making available methods to analyze horizontally partitioned data was the massive data setting. But everywhere in the massive data setting, you have control over the distribution of the data across nodes, which you don't when you deal with healthcare data. So with healthcare data, you mostly have predictors that differ from site. So the distribution of the predictor usually differ from site to site. Okay, so it is not realistic to assume that the data are ID across sites. But a much more realistic assumption when we're talking about regression would be that there's a common model for the distribution of the response given the predictors, but the distribution of the predictors may vary. Okay, so that would be to say that you assume that the link between mortality and other factors is the same across nodes, but the distribution of those factors, for example, age, may differ between sites, between nodes. Okay. So as I mentioned, most methods that were made available for this type of data, they were put forward in the massive data setting. So they do not handle uneven distributions of the data between nodes and heterogeneity in the predictor distribution in the nodes. But making the adjustment when you know a bit about statistical theory is not that difficult. So what we did is that we tweaked those methods to make them work for uneven distributions of predictors and uneven sample sizes. And then we will compare them in terms of information sharing requirement and their operational complexity. So first we'll see what are the challenges that needs to be overtaken when we think about statistical inference procedure with horizontally partitioned data. Then we'll see the methodology that we employed and the results that we obtained regarding the identification of the available approaches. And we'll give a brief overview of their applicability, and we'll compare the available methods to analyze to make inferences using a GLM model, a generalized linear model, which includes the linear regression and the logistic regression model that are commonly used in healthcare. So to present the challenges that are that you may encounter when you want to use statistical inference procedure, you must know what is what are we talking about when we say statistical inference. So what is statistical inference? It is usually defined as the set of techniques that for inducing the unknown characteristics or which are encoded in the statistical model as parameters of a population from those observed in a sample. So you have a population and you want to interrogate the population, and you're trying to estimate parameters from the model that you pose on your population using a sample of that population. Sometimes identifying the target population. So sometimes we have the reverse problem. We have a sample and we want to we're not actually sure what from what population comes from that sample because you haven't controlled the sampling process. But this is another topic. So to do this, you need to do a probabilistic modeling of the system. So you need to pose a model. For example, the data that for example, the data that I have been generating under a generalized linear model. Okay, and then you wanna do parameter estimation, but you also might want to compute confidence intervals and make statistical tests in order to quantify the level of uncertainty in parameter estimates. Okay. So the basic of statistical inference is that you wanna assess how much the trends that are observed in the sample are representative of the trends that you would found in the population. So we're talking about between samples variability. So this is when you're trying to assess with confidence interval. So this is the statistical inference that is illustrated. And I'm illustrating this because so you have a population and then you sorry about that. So reactive, my mouse. Okay. So you have a population from which you draw a sample. So as I said, often in health, when we're talking about analysis of data that observational data, sometimes you don't control the sampling process. So you have a sample and you're not sure from what's the actual population that is represented by that sample. And then you pose a probabilistic model. So for example, the relationship between a response and the predictors is linear. So this is an example. And the regression residual is Gaussian. So this is an example of a probabilistic model. And the probabilistic model, it tells you something about the sampling. So for example, the data is IID. As I mentioned, when we talk about horizontally partitioned data, so data that come from different nodes, it is often unrealistic to assume that all the data across nodes are IID. But maybe a more realistic assumption would be that the distribution of the response giving the predictors is the same across nodes, but the distribution of the predictors might vary across nodes. Okay, so the probabilistic model will be influenced by the fact that you are analyzing horizontally partitioned data. And the model fitting as well, because when we talk about horizontally partitioned data, you cannot store the data at a single location. So you only need to proceed by exchanging summary statistics from site to site. Okay. So this is a slide that's basically writes down what I've just said. In the presence of the horizontally partitioned data, you need to modify a bit your probabilistic model to take into account the fact that the distribution of your predictor across nodes might be different. And the fact that you will need to tweak a bit the model fitting because you cannot centralize the data set and use the usual algorithms to compute the confidence interval and to make the appropriate test. So so they should be carried out following the exchange of summary statistics between site and the coordinating center. And the probabilistic model, it must take into account of possible imbalances in distributional characteristics. So what we did with this work was first to do a scoping review of the literature to see what of the methods that are available to analyze horizontally partitioned data, and we haven't restricted that to with the application to healthcare because we as I mentioned, it is usually doable to adapt the existing method to take into account imbalances in sample sizes and heterogeneity between node to node predictor distribution. And then from those, we assessed which ones were applicable to GLM-based analyses. And we assessed their operational assumptions. So what are the assumptions that must be met in order to use this method? Do I need to have IID data to use their algorithm? If not, then we proposed, we use statistical theory to make it appropriate adjustment to make them usable in healthcare data. And from there, so we designed from each method that we found, we designed an algorithm that makes them applicable to the context of healthcare research. And from that algorithm, we compare the operational complexity and the information requirements of each of the available methods. So we found 41 articles that came mostly from the literature on massive data analysis, but not only. Some of them were specific to the healthcare data context. And we found four. We called these four operational workflows. So these methods, they could all be correct. They could all be they were all, we could all classify them into 4 operational workflows. So the first one, it's the meta-analytics. So the two-stage meta-analytic type of workflow. That is, we ask each node to send once a set of information to the coordinating center, which aggregates that information in order to produce the result. In the second workflow, so in the second workflow, can you see my mouse? Yes. So in the second workflow here, there are iterations that are authorized between the coordinating center and the nodes before producing the final result. And these two are a bit more complicated, because here you can see that there's a site that plays a role, I would say an asymmetric role compared to the other sites. And these methods, for those who knows these type of frameworks, they were found in all the methods that were based on surrogate likelihoods, okay, which have been applied in the healthcare context. So the approach that we found that were applicable to GLM-based analyses, you can find we found 6 of them, and you can find 5 of them here. The simple averaging, which is the meta-analytic type of approach. There's a method that requires only 2 rounds of communication between the nodes and the central server. So it basically, so this is the single distribution Newton-Raphson updating, and this is basically equivalent to making the first one, so the simple averaging, and then do a distributed Newton-Raphson updating. So basically asking each site to compute a gradient and a Hessian, and then send this back to the central server, which then computes the Newton-Raphson updating, and then the output is so the result comes from that after the Newton-Raphson updating. The third one is the multiple distributed Newton-Raphson updating, and this has been encoded so in a data shield, which is a software that allows to do distributed analyses based on GLM. There's the fourth one was probably the most for a statistician. The fourth one was probably the most interesting one because it works with the meta-analytic workflow. So 1 round of communication between nodes and central server. So just has, but in some cases you recover so the same information that you would have by centralizing the data, but using only 1 iteration. So all those methods, they rely on a local parameter estimate of the model and sharing gradient and Hessian of the log likelihood function. But they differ in terms of the number of iterations that they required and how quantities sent by the nodes are combined at the coordinating center level. Of course, I'm not going to show the algorithms, but so when we assessed the underlying assumptions of the method, we found that the methods that were proposed all assumed IID data and homogeneity of the distribution across sites. So what we did is that we adjusted those methods to make them appropriate to the healthcare context. So this is just a proof that we did the algorithm. You can see those in the paper, but I'm not going to go through the details today. And we produce a table like this to compare each of the methods that we identify with the corresponding workflow and the quantities that were shared. So conclusions, things to remember from my talk today. So to conduct statistical inference method based on horizontally partitioned data, there are several methods that exist. They differ according to the amount of information that is shared and the operational scheme that they use. For example, the number of communication between the nodes and the coordinating centers, and the quantities that are shared, and how the coordinating center aggregates the information sent by the nodes. Second point, some statistical inference procedure, usually performed using a centralized database, can be equivalently performed on a decentralized data set. So they produce the same result. And this is the case for GLM-based analysis when you use the multiple Newton-Raphson updating, or when you're using, for example, a linear regression model and you use the estimating equation algorithm. Third, meta-analysis methods, they can be used to analyze data stored in different locations, but they are usually not the most powerful methods to do so. And the fourth one is that it's the same. So the fourth one is just a general warning that we have the same issue of target population identification that the one that you would have by centralizing the data from by centralizing multi-site data, which means that sometimes when you use data that were collected in different environments and you pool them, then it is hard to really see what's the target population that from which your sample actually came from, and this has impact on the conclusion that you would draw from your model. So I'm going to stop there. Thank you very much again for the opportunity to present my work, our work.
Thank you very much. Our next presenter is Dr. Nichole Austin.
Okay, can everyone see my slides, hear my voice? Fantastic. Okay, thank you very much for having me today. I'm really excited to be here and talk about some of this work that our team has been pushing forward with for the past couple of years now. Time flies when you're having fun, right? So my name is Nichole Austin. I am based at Dalhousie. I have cross appointments in community health and epidemiology and obstetrics and gynecology. I will preface this presentation by saying I am not a biostatistician, nor am I an economist. So the work that I'm presenting today, a lot of the technical aspects have been really undertaken and led by the economists on our team. I am a user of this particular method, and so that's sort of where I come into this team. So I will do my best with the technical details, but do expect a higher level over what you might have heard from one of our economists had they been here in my stead. Today, I'm going to talk about advancing difference in differences for unpoolable data and introduce you to a new method that we've developed, which we refer to as UNDID. I'm sort of picking up where Félix left off a bit with this idea of horizontally partitioned data. Some of the language that we use is slightly different, but the ideas are exactly the same. So we're in a situation where we have different nodes holding different data, and these data can't be combined for analytical purposes. So a pretty common challenge for many of us. So folks like myself who are interested in policy evaluation are really invested in learning from different policy shifts and different sort of jurisdictional issues policy-wise across Canada, across countries, across other jurisdictions. The issue that often comes up for us is that health data, as we've heard already today, and as most of you probably already know, health data tend to be unpooled across all of these jurisdictions. And this results in a lot of analytical challenges. So once we are no longer able to pull the data, we are restricted from using a lot of the analytical methods that we like to lean on, particularly those of us who work in policy analysis and policy evaluation. We use a lot of difference in differences. And I'm going to explain what different diff is in just a minute for those of you who don't have a background in this method, but it is one very common method for policy evaluation, which it turns out up to this point was pretty difficult to use when the data were unpoolable. And actually this work was motivated by a concrete limitation that our team, one of our previous teams encountered, where we were doing this evaluation of primary care reform, and it was a comparative analysis looking at Ontario and Quebec. And we had initially set out to use diff and diff for this comparison, and both we were using admin data in both provinces. But the fact that we couldn't pool these data actually stopped us from doing the analysis that we wanted to do. And so that right there was enough to motivate us to seek funding for this work and to move forward with this particular project. So today what I'm going to be talking about is sort of the rationale for this overall project, which I've already introduced. And we'll talk about two aspects. So first, the development of the analytical framework for estimating the average treatment effect on the treated, or the ATT, using difference and differences with unpooled data. And again, we refer to this as undid. And I will also talk about the validation of this framework. The economists use some Monte Carlo simulation for their validation work, and then handed things off to us for some real world pseudo-siloed data. So I'm going to talk about both of those validation experiences. So a very, very quick overview of what difference and differences is. Again, I think many of you are probably familiar with this, but just so that we're all on the same page moving forward. The intuition is actually quite straightforward, despite what this image suggests. So the red line here is our treated group, right? So we're observing some treated group over time. We're starting in 2010, going all the way until 2020. Treatment occurs around here in 2015 for the treated group only. So in 2015, let's say there's some policy shift, some exposure that leads this group to be considered the treated group. You can see after 2015, the trajectory of the outcomes in the treated groups changes, right? So we go from this trend to this more upward trend. This is all well and good. You could do a pre-post analysis looking at what happened, post versus pre-intervention in the treated group alone, but that fails to account for any underlying temporal trends that we often want to take into consideration analytically, because these are often informative and can lead to bias if we just don't deal with them in the analysis. So what diff and diff does is introduces this control group in blue at the bottom of the plot. And the control group really stands in for what would have happened in the treated group had they not been treated. So this is our counterfactual. There are many assumptions to be met when you're using this method, but this is the basic idea. So essentially what we're doing with difference and differences is we're comparing what happened in the post period in the treated group versus the pre-period, and then differencing out what happened in the post control group period versus the pre-period. And that gives us our ATT. Which you'll see on the next slide is equivalent to the beta-3 coefficient that we're often interested in difference and difference. So again, many assumptions need to be met and checked to use this method. But up until this point, the one that wasn't explicitly stated was poolability. So the ability to bring all of these data together into a single data set for analysis. So what our team has done is added that formally as another assumption that's required in order to conduct difference and differences analysis. And then our workaround is intended to deal with cases where poolability cannot be met. So just to contrast conventional difference and differences with our novel undid method. The basic formula for pooled diff and diff, assuming repeated cross-sectional data and covariates, is as follows. So fairly straightforward linear formula that I'm presenting here. Things get much more complicated in almost every setting, but just to give us a starting point. So our outcome is some function of the intercept term, the treatment coefficient, the coefficient on the post period, this interaction term between treatment and post-period. And again, that beta-3 is often what we're really interested in when we're conducting difference and differences analysis, plus beta-4, and that's some vector covariates, and our error term. Now, interestingly, what this is going to give us is one coefficient per covariate common across silos. You can think about relaxing this constraint. We often don't do this in difference and differences, but you could by letting these coefficients for the covariates vary by silo or by group. You're going to see this language in this presentation of revised pooled estimators. And when I say that, this is what I'm referring to, that introduction of a little bit more flexibility for those coefficients on covariates rather than one common coefficient. Once our economists figured this out and started thinking a little bit more about this, they realized that this novel undid estimator, this extension to difference and differences for unpoolable data, is essentially an extension of this idea of the revised pooled approach. So allowing these coefficients to vary across silos, and then doing some silo-specific regressions and bringing everything in together all at the end. So here's the basic intuition behind this novel method, behind undid. Again, we're in a situation where we cannot pool these data for analysis. So we're going to start there and deal with everything within silos, within provincial silos, for example. So we'll start with silo-specific regressions. In this case, we're going to go to each individual province that's involved in the analysis, and we'll look at their pre-coefficient, the post-coefficient, their beta 3, so the vary coefficient. And then the silo-specific differences are going to be equal to that difference between beta 2 and beta 1, right? So the post and the pre, and that gives us our deltas within silos. The difference in difference estimate, in this case, in the undid case, is the difference in the treated group minus the difference in the control. So that's our ATT. The standard error estimation is a little bit more complicated. So the ATT is relatively easy to recover in the silo case, but we knew going in that the standard errors were going to be the bigger part of the problem, the bigger challenge. So the standard error will be the square root of the sum of squared errors for the coefficients used to compute the ATT. As I mentioned, the economists on our team wanted to move forward with some Monte Carlo simulations just to see how well this performed under a range of different conditions, basically. So to give you an idea of sort of what we're talking about before we go into the simulation work, this is the schematic that we've been using since the beginning of this project. So on the right-hand side, you have conventional difference in difference. This is what happens in the conventional case. So you have some treated silo, say a province that had a policy shift, and then you have an untreated silo, province that didn't have a policy shift. In this case, fortunately, the data are poolable. So we can just bring all of these data into a pooled data set, assuming, as Felix mentioned, that everything is harmonized, everything is beautiful and synced, and we don't have to do any of that work. We'll assume for the sake of argument here, everything just comes together into a pooled data set. With this data set, we can go ahead and move forward with conventional difference in differences, and that gives us our pooled ATT. So this is usually what happens for folks who use diff and diff. On the left-hand side is the situation that we're trying to address in this work. So this is the unpooled case. In this case, the treated silo and the untreated silo cannot be combined into a pooled data set. So we have our treated regression and we have our untreated regression. Right, so we're going to get a difference in parameters for both of these. And then the difference in these differences is what will give us the ATT. So the hope going in was that these two ATTs would be equivalent. And that is what the first step of the validation work set out to figure out. So this is a very, very brief summary of the Monte Carlo simulation. There is a paper that I'm citing at the end of this presentation that was actually just released, I think, a week or two ago. So for the full technical details, I would urge you to take a look at that paper. It's much more quantitatively informative than what I'm showing you today. In short, for the Monte Carlo simulations, we are dealing with a relatively simple set of scenarios. So 2 groups, 2 time periods, the very basic diff and diff setup. We simulated some data, so 5,000 individuals per group, 10-year time period, and treatment occurs in group 1 in year 5. So we have that treatment, sort of the same vertical line that I showed you in the initial diff and diff plot. Occurring at year 5, only in group 1. We're using 1,000 replications per case, and then there was a little bit of playing around with the balance of sample sizes, increasing the group number, etc. In terms of the simulations themselves, we started with the simple case with no covariates, just to see how things performed. And then we introduced time invariant covariates and got a little bit more complicated with time varying covariates and assessed performance of this novel method in all of these different conditions. So to give you a general sense of our findings, this novel method performed really, really well without covariates. So it yields identical coefficients and identical standard errors. Once we introduced time invariant covariates, things started to change a little bit, and I'll show you what that looks like on the next slide. So the coefficients were identical that we were recovering from this method versus conventional diff and diff, but the standard errors diverged a little bit. However, things started to converge as the sample size increased. Once we introduced time variant covariates, we saw a little bit more variation, right? So in this case, we're seeing similar coefficients in standard errors. The coefficients are no longer identical, but we're pretty close still. So we were still quite happy with the performance. And again, both of these are going to converge as sample size increases. So these are some plots taken from the paper that I mentioned a minute ago. You'll see the citation to that in a couple of minutes. On the left-hand side, you are looking at standard errors comparing conventional diff and diff estimates to our unpooled, undid approach. And we're setting here the true ATT at 0, and then we're introducing a little bit of an effect, so setting that ATT at 0.1. You can see that these track pretty well together. However, if they were equivalent, you'd see a nice 45-degree angle, all on the same line. So there is a bit of bouncing around here. On the right-hand side, you can see what happens as we increase sample size. So again, this convergence that I mentioned on the previous slide is evident when you look on this right-hand panel. As the sample size increases, all of these standard errors, or sorry, these are the mean squared errors, are converging. And so this is really reassuring to us. So after the economists on our team had conducted some of this preliminary validation work, we thought, well, that's super interesting and really encouraging, but simulated data are simulated data, right? So what happens when we apply this to real world data? So that's what the team, sort of the group of our team members that I lead, set out to do. So we use the Canadian Community Health Survey, the CCHS, which, as most of you probably know, includes all provinces. And so this is an example of a pooled data set, but it can be analyzed as if the provincial data were siloed. So we use the CCHS to create what we call a pseudo-siloed data set, where we had the advantage of knowing, by definition, what the true answer was, but we could play around and pretend that these data were siloed by province. In terms of applying this approach to this data set, we decided to do a conceptual replication. So we're not aiming to precisely replicate the initial effect estimates or anything like that, but it's a conceptual replication of an existing analysis looking at the effect of provincial screening programs on colorectal screening uptake. So just to give you an idea of what this analysis looked like, they were comparing the effect of provinces that mailed screening kits upon patient request in PEI to New Brunswick, which served as the control province. 2 periods, again, pretty simple diff and diff setup. So we have 2003 to 2010, which is our pre-intervention period, 2011 to 2014, which is our post. What we're assessing in this replication was the program impact on lifetime screening uptake in patients aged 50 to 75. We compared a few different differences estimates. Difficult to say. First, we started with the conventional diff and diff, because again, this is a data set. We have everything all together by design because it's CHS, so we could very easily generate that conventional diff and diff estimate. We then, as a middle ground, we ran a revised pooled estimate. So again, this is where you allow those covariates on the coefficients on the covariates to vary by silo or by province in this case. And we ended with this novel approach, this undid method that we've developed. There were several covariates, I should mention. So we had sex, which is a binary variable in the CCHS, education, which was also binary for the purposes of this analysis, age, which was continuous, and income, which is categorical. So a few different types of covariates, and the distribution of these covariates varied by silo as well, by province, which is sort of an added layer of complexity versus the initial validation work that our team did. To give you an idea of how close we got to the original sample, because this was a conceptual replication paper, we quickly discovered that it is challenging to precisely replicate existing work in the absence of somebody else's analytical code. So I've done a bit of replication work before. I knew that this was going to happen. So we're not exactly lined up with that initial sample or the original sample, but we came pretty close. We were relatively pleased with this, just being able to pull a very similar sample together based on the description of the paper alone. The one exception is education. So this is the one characteristic that we really couldn't match closely despite our best efforts. And here is probably the least exciting plot I've ever put together in my life. So this is our model comparison, showing you what happened when we're looking at the conventional versus the revised pooled versus the undid method. So our 3 different flavors, essentially, of diff and diff. I'm showing both unweighted and weighted estimates here, just to give you a sense of whether that made any changes, any difference. And it really didn't. You can see that compared to the conventional estimate, our undid approach performs very, very well. We're getting quite close to that conventional diff and diff estimate. Same for the standard error. So again, a little bit of difference, but even in a case where we're using real world data and covariates of different forms that vary by province, we are still able to come quite close to that conventional diff and diff estimate, even without the benefit of a pooled data set. So here's where we currently are. We've come to the conclusion that UNDID, this novel method, performs very well under a range of data generating processes and model specifications, which is really reassuring and exciting to folks like myself and my teammates who do a lot of policy evaluation work. We also think that this method should be reasonably easy to implement, even in secure data environments. And this was key for us from day one, because all of us have worked in RDCs, we have worked with administrative data. We are very familiar with the barriers to working with these types of data and to working with analysts who are sort of housed within these data facilities. So we know that whatever we develop has to be very easy for folks to run. And so that has been key. And we think that we've actually landed on something that will tick that box. We also believe that this will allow researchers to leverage policy variation, even in unpoolable data contexts, which in the Canadian context certainly is extremely exciting, but the same could be said for many, many other contexts across the world. And here's a link to the paper that I've been mentioning throughout this presentation. So again, we just put this out there a couple of weeks ago. We would certainly welcome any comments. It is up there as a preprint. Looking ahead, just to give you an idea of where we're going next with this work. So we are actively developing a software package in Stata and hopefully in R to automate all of this. There would be also an accompanying user guide, so all of this work is in progress. We were not able to address every nuance of and every potential challenge of diff and diff in our work to date. So looking forward, we do hope to address staggered adoptions. It's something that often happens in diff and diff. There's a bit of work in that paper from the previous slide on staggered adoption. This is definitely an avenue for further exploration. Cluster robust inference. So Matt Webb, one of our leads, is an expert in this area and very keen, I think, to move this method forward in that direction. And finally, nonlinear models. So this method that we are putting out there can really only accommodate linear models at this point. So just a word of thanks to CIHR for funding this work, to our awesome study team. It's led by myself, Erin Strumpf, and as I just mentioned, Matt Webb is leading the economics side. And we also have 2 students and research assistants who are driving this work forward. So we're very grateful to all of them. Thanks very much. I'd welcome any questions.
Thank you both to Félix and Nichole for fantastic presentations. So much information in what you both just provided. And I see that there was a question for Félix, and you've already responded to that in the chat. And there's links in the chat to both of the papers that were referenced during the presentations. I'm just going to do a quick look. I'm not seeing questions coming in, I think because there's a lot to take in. And we don't have a lot of time. So I want to pose just a very quick question for each of you to answer, which is, what do you think are the most important next steps, given what you have done already? So Félix, if you don't mind, I'll go to you first for that.
The good question. I think there are still questions that needs to be answered. For example, we usually when we talk about statistical inference methods for horizontally partitioned data, we say these methods are generally privacy preserving, but of course this depends on the number of covariates that you are using within each site and the number of individual samples that you have. While for many research questions, you would have many individuals within each node, which would then probably make the method privacy preserving. If you're thinking about a context like rare diseases, where you have very few individuals per node, then this might be a problem. So I think there might Yeah, I think at some point, maybe the privacy question should be looked through the lens of, for example, differential privacy, which is a criterion that has been used by many big companies like Google to quantify the degree of information that the summary statistics is shared. The degree of information about one individual that the summary statistics that is made available shares. And then, of course, there's also the question of vertically partitioned data, which sometimes needs to share, for example, the response variable. But in contexts where this cannot be done, then perhaps there needs to be adaptation to make them work for healthcare data.
Great, thanks. And Michael, I'm sorry, we're not able to unmute you, so I feel it'd be great if you are willing to type out a question in the chat. And Nichole, same question to you, but there's also a question in the chat about whether you know or believe that what you've done in diff and diff would be generalizable to interrupted time series analysis.
Yeah, let me tackle that one first. So with interrupted time series, there's usually not a comparison group. So I'm not sure that we would really encounter the same issue with not being able to combine silo-specific data, but maybe I'm misunderstanding the question. In any case, it's not something that's come up with our team. Certainly, if we think about something like controlled interrupted time series, then I think we're maybe in the same ballpark. But for standard ITS, we haven't really discussed that. In terms of like priorities, next steps, and all of that good stuff, I think for us it's probably twofold. So the one of the key priorities is getting this data package out and together and creating something really usable that actually solves an analytical barrier for like so many people doing this type of work. So I'm really excited about that. I think the other priority is really this question of covariates, right? So this has come up in our team. We're actively discussing this, and just this idea that for so long we've really just been condensing that coefficient on covariates to one thing across, very potentially disparate silos, disparate situations in each province, and thinking a little bit more about like whether or not that's appropriate and whether or not we've sort of been injecting some bias into conventional differences. I think that that's a really interesting thing to consider, and one of the more exciting things that's come out of this project.